this is really kind of a motivation, a presentation here, both in terms of like, okay, how do we look at detrital geochronology age distributions? And then what happens if we want to look at many distributions at once and try to compare them visually? And we'll see toward the end how that kind of breaks down when you get a lot of data in one place. Joel already went over this. As far as questions go, again, just direct them toward Joel, Sam, or Glenn. And if something's pressing, then they can go ahead and interrupt me, or anybody can interrupt me anytime, really. Cool, so here's our course schedule. Again, Joel went over this. This is kind of, let's call it module 1. So detrital geochronology data visualization. So the outline here, first I'll talk just briefly about what detrital geochronology is and what we can do with it, and just kind of a one-slide deal. The major learning goal here is to understand the basis for visual representation of detrital geochronology data. So how do we actually look at these things? How do we even calculate age distributions from numerical data? So histograms, probability density plots, I'll call those PDPs, you might hear me say that. Kernel density estimates, KDEs, and also cumulative distribution functions, so CDFs. Okay, first off, all right, what is detrital geochronology? So this is a technique most often a geoscientist, some earth scientist will go out and sample some sedimentary rock. So here's a siliciclastic rock, and they will extract the zircons out of that rock. So these zircons are pretty small. Here's a scale bar, 100 microns, so about the width of a human hair, so pretty small. And what the researcher does is they'll take these zircons and they will date them, typically using laser ablation ICP-MS because it's the cheapest and the fastest way to do this in terms of sample throughput. And the researcher will analyze tens to hundreds, even thousands of individual zircon grains from this rock, typically at random. And what the researcher obtains is a population of ages, so, or rather a distribution of ages. You can think of the distribution as a representation of the underlying population that is inherently unknowable, because you would never be able to analyze every single zircon in, say, a sedimentary formation. So we're trying to get an estimation of that. We're trying to get a representation of that underlying population. The researcher will use this information to say something about sediment provenance. So where did those zircons come from, and likely the sediment along with those zircons. And also maximum depositional age is often is another really powerful tool here, because the zircons have to be older than the rock that they're contained in, right? Kind of like the chocolate chips in a chocolate chip cookie have to exist before you make the cookie, right? So these zircons can provide a maximum depositional age. So we can look at these in a number of ways. Here's an example. I just made this data up, and we have 6 ages. And so here's just a kind of a classic histogram. You'll see a lot of plots like this. All of them will have this axis here on the x-axis goes from 0 to 2,000 million years, so 2 billion years. And here we have 6 ages. So probably not the best representation of the underlying population, but this will work for an example. Again, typically people will go and measure at least 100, if not a few hundred. And in some cases, if it's a really complex distribution and they have a lot of funding, they might do thousands, like they do sometimes in the LaserCon lab here. So here we have, again, 6 ages. So 500 million years, we have 1 age, so count 1. 750, we have 1 count. 1,000 million years, and then we have a few ages in this about 1,500 million year range. But most often people don't look at these as histograms these days. What we do is we actually convert each of the individual ages into a Gaussian curve. So again, here are those 6 ages. So 1, 2, 3, 4, 5, 6, and the width of those Gaussian curves is set by the analytical uncertainty here. Okay, so because uncertainty is going to scale with age, the younger ages are going to have a smaller uncertainty, and the older ages are going to have a larger uncertainty. So kind of wider, broader peaks out here. Can you guys see my cursor? Just somebody give me a yay or nay?
Yes.
Yay.
Yes.
Okay, cool. Thank you. Yeah, so wider peaks out here and spikier, kind of taller peaks out here. Each of these Gaussian curves sums to 1. So underneath each of these curves, that integrates to 1. And I've put the math up here for Gaussian, but that's really just for reference later on. I'm not going to dwell on any math in this presentation. So what we do is we actually add all of those up and renormalize. And so now we've added all 6 of those Gaussians together and normalized, basically divided by 6. And now we have, under this curve, we have, it sums to 1. And now we have an estimation of the, call it the probability of obtaining another one of these ages, if this were a reasonable representation of that underlying population. Clearly, we'd probably want to analyze more than 6 grains, but if you're tight budget, that might be all you got. A point to make here, and this will be important, particularly for some stuff that Joel's going to talk about, I think in the next module when we start talking about how we actually quantitatively compare these. These aren't continuous functions, but rather they're discretized functions. So really, these are just points along an x-axis. So these are y-axis values along an x-axis. And so they're, at the end of the day, they're a one-dimensional array of data. Okay, and that's going to be extremely useful for some of the quantitative metrics, or really all of the quantitative metrics that use probability density plots or kernel density estimates. So again, they're discretized functions. So that was probability density plots. So kernel density estimates are a little different. And here, instead of using the analytical uncertainty to set that width here, to set that width of the Gaussian curve, you specify a bandwidth instead of that. And you set, in this case, you set the bandwidth equal for all of these 6 states. And so notice that now they're all the same height, right? Okay, but we do the same thing if we add all of those together and then normalize. Now we get what's termed a kernel density estimate. And again, the area under this curve is 1. Okay, and so the strengths and weaknesses of probability density plots and kernel density estimates of PDPs and KDEs will hopefully become apparent in a few slides when I start showing examples of real data. Another useful way to visualize age distributions is a cumulative distribution. So here's an empirical cumulative distribution. And so this, when you zoom in on these guys, they look real stair-steppy like this. And what you're looking at is, maybe this will help if I put the ages on there from the KDE. Every time you have an age, basically you take a step. And so we'll have 6 steps in this cumulative plot. And it's basically a running sum of those dates. So at 500, you take a step, at 750, you take a step, and these are equally spaced along the y-axis. And that's really useful because now we can start talking in terms of probability. So note that the probability on the y-axis now goes from 0 to 1, whereas before, here it's some tiny number because under these curves, that has to sum to 1. So you end up with some tiny number here, but on a cumulative plot, it just goes to 1. And the way you can think about this is, say this was a perfect representation of of the age distribution or the underlying population. You can say at 200 million years, there's a 0% chance that you're going to find one of those ages if you analyzed another grain. Whereas if you go to say 1,000 million years, and then you track that here, there's the third stair step, you have a 50% probability of obtaining another age that's younger than 1,000 million years. So these, I really like cumulative distributions. I think they're really useful. And this, again, their strengths and weaknesses will be apparent here in just a minute. But I want to pause there for just a second and maybe field a couple of questions or go back to a slide if anybody has any questions. I have plenty of time for questions here. Crystal clear? All right, then I'm going to press on. Okay, so how do we deal with multiple samples? It's what this course is all about, right? Like, how do we deal with multiple samples? And we won't do this in a quantitative way, but by the end of this presentation, hopefully it'll become clear why we will want to do this in a quantitative way. So let's take a classic example from George Garrell's work. He's my postdoc advisor here at Lasercron. George did this awesome study in 2011 where he went and he sampled all of the sandy packages in the Grand Canyon through the Paleozoic section of the Grand Canyon. If you're, forget somebody yesterday in a meeting said if you're not familiar with the Grand Canyon, it's this big hole in Arizona. I kind of liked that, but so yeah, here's basically where we're going to go from the Tapeats all the way to the Kaibab. So bottom of the section to the top. And so here's a representation of that using probability density plots. The cooler colors are the bottom of the section, and the warmer colors are the top. And so we have 25 samples here. And you can see this already gets a little unwieldy, right? Like it's a little hard to interpret this in a visual way. And so we have, you might be able to pull out of this, okay, well, there's, I don't know, the lower section might be defined by these two broader age groups or age modes here. And then it kind of gets a little more complex as you move up section. And that's about, I mean, all you can really say. Maybe get some younger ages toward the top of the section, which might make sense, right? Another way people look at these data is to take that plot apart, excuse me, and stack the probability density plots on top of one another. And a nice way to do that is to do it stratigraphically. And if you've perused around the tetraedral zircon provenance literature, I'm sure you've seen tons and tons of these types of plots. But again, we're going from the bottom of the section to the top. And yeah, you could probably pull out that, well, okay, it's pretty simple. We have these two distinct age modes at the bottom. Then at about sample, I don't know, 5, 6, whatever that corresponds to in the Grand Canyon, we start to see an introduction of younger and younger age groups. But still, at the end of the day, how different is this top one from the one below it, from the one below it, and so on? And so be hard pressed to make any detailed interpretations without a bit of subjectivity. Kernel density estimates here. So remember the difference between a PDP and a KDE. That PDP incorporates that analytical uncertainty. So you'll see some spikier, typically see some spikier peaks out in the younger part of the age distributions and a little more washed out in the older. Whereas a KDE, remember those, each individual Gaussian is has the same bandwidth. And here would be kind of a wide bandwidth, so 25 million years. And you can see that the younger part of this, these age distributions in the top left here they get a little washed out. I'm going to flip back and forth just so you can kind of get a sense of that. And you can play around with the bandwidth. It's an arbitrary parameter unless you use an optimization method, which there are a few out there that are useful. I tend to stick with a set kernel bandwidth for reasons I think Joel's going to go over in his slides. But now, just for demonstration purposes, this is what a 10 million year would look like, that data. So 25, 10, and you can get crazy with this and say, well, probably 2 is a little small, right? And so it gets really, really spiky. But the goal here is really, like, you just want to visualize your data. You want to be able to say something. Maybe you don't see what you want to see in this 25 million year, with this 25 million year bandwidth. Maybe you see a little more detail with the 10, and then 2 is maybe just a little ridiculous. So it's really a judgment call there. So here's CDFs, and I'm showing these in a similar way that that I showed that kind of stack of PDPs initially. But what's nice about CDFs, I think it's a little easier actually to interpret, say, broad changes. So just like we saw before, we have this major kind of group of ages around 1400 and maybe around 1600 million years for the lower part of the section in cooler colors. And then we get an introduction of these younger age groups higher up in the section. But again, it's going to be a subjective interpretation for everything in between, right? So these kind of, as you transition from cool to warm colors, saying which distribution is more similar to some other distribution is, again, you're going to run into a lot of subjectivity. It's hard to treat the comparison in an objective fashion.
Hey, Kurt.
Yeah.
I'm going to jump in. Can you, I think we've got the time and there have been a few questions. Can you go over or more fully explain bandwidth, uncertainty, and how those are used calculating PDPs and PDPs? Because I'm actually not going to get too deeply into that in my presentation. And again, there have been a couple questions about it.
Yeah, sure. Cruise back. Okay, so again, each of these individual dates, let's just take this 500 million year date. So that's, you take one zircon from the rock, you analyze it, and you get, say, 500 plus or minus, I think I gave it like 10 million years. Again, I made up this data. And so at 1 sigma, that's going to specify the bandwidth. Say it's plus or minus 5 million years. At the 1 sigma level, so if you think of a normal Bell distribution, this is where a whiteboard would be really helpful right now. You could, at 1 sigma, I think I could draw, right? Do I have a pen? Red. Oh, cool. Okay, so I'm going to try to draw this. Whoa. So this is supposed to be a bell curve. Can everybody see that, or anybody? It's a really not the greatest bell curve.
Yes, we can see.
Yeah, we can see what you're doing.
Cool, thank you. So 1 sigma, so this is the mean median mode. At 1 sigma, so at 68% of that, it's going to be rough. That's going to be 1 sigma. Right, 1 sigma. So that's 68% of that area. And that's, yeah, that's 1 sigma. At 2 sigma, you get 95%. So you're just barely cutting off the tails here. So this would be 2 sigma. And that's just 2 times 1 sigma. 2 sigma. Cool. And so this probability density plot is made with uncertainty, say, at plus or minus 5 million years at the 1 sigma level. So that would be like, okay, 5 million years that way and 5 million years that way. And at the end of the day, if you wanted to create the probability density plot with 2 sigma uncertainties, you would end up with the same result, because the 2 sigma uncertainty would be plus or minus 10, right? Because 5 times 2 is 10. So this would functionally come out to look exactly the same, because this would, if you constructed it with a 10 million year plus or minus uncertainty here. And the point of, so that's for a probability density plot. So basically each individual date will depend on the analytical precision that you get from the laboratory measurement. The KDE will take each of these. I'm going to move on. I'm probably going to lose all that. Oh, it stayed. Okay, cool. So here, that that's probably not 1 sigma, but it's a pretty tall distribution. So that would be, say, 1 sigma and 2 sigma. Maybe it's probably closer to something like that, right? But the point is, these are all the same. These widths, kernel bandwidths, are all set exactly the same. So basically, at the end of the day, the KDEs do not take into account analytical uncertainty, excuse me, and the PDPs do. Further, the CDFs, these cumulative distribution functions, only take into account your best estimate of the age. So typically your mean age. So each of these does not take into account the analytical uncertainty. How's that, Joel? Will that suffice for what you need?
Yeah, that's perfect. Thank you.
Okay, back to the Grand Canyon. Who doesn't want to go to the Grand Canyon? Okay, I think I have about 8 minutes left. So let's see. So where was I? Okay, so KDEs, yeah, I like KDEs, particularly if you have young ages. And a good example of that, see, I already showed this, would be here. So this is some work that I did actually as a PhD student with Joel. I'm not going to dwell on the geology too much, but this is in the Central Andes. should have put a map of South America here, but we went out to the Altiplano and got some Cenozoic sandstones, and we wanted to figure out where those sediments came from. And so we went all over the place, dug through the literature, sampled our own older potential sources, which are shown here in these age distributions. And we wanted to say something about the sediment provenance of those younger Cenozoic deposits. And I'm not going to dwell on the geology, but the first thing I did when I was looking at these data, like Joel sends me to the lab, and I just overnight in the lab many nights, and then I produce all of this data and try to look at it, and this is what I get. So again, we're going from older to younger. These are Paleozoic samples down here that likely sourced these younger Cenozoic samples. And you see an immediate problem here, right? These younger part of the age distributions for the Cenozoic samples are completely dominated by this really tall spike. And that's because the analytical precision is better for the younger ages. And in the Andes, it's an active continental arc. So you have a lot of active volcanism going on throughout the Cenozoic. And so this just dominates the signal. And one of the things that we wanted to say something about was, well, we want to know about the provenance, but you can't see anything. It kind of flatlines as you go away from the Cenozoic, as you get into older and older parts of that distribution. So this is where a PDP might not be the best idea, right? Because this is really spiky in the young ages and pretty subdued and washed out in the older. So KDE helps with this a little bit. So here you can see that this kind of drops those peaks down. And again, we're treating every single young age with as if it had 25 million years uncertainty. Okay, and so you start to see a little bit more out here, right, with the KDE. So kind of pick your poison here as far as visualizing the data, but I think KDE does a little bit better job of at least showing some of the older part of the age distribution, particularly for these younger Cenozoic samples here in these cooler colors at the top. Here are CDFs. So again, even though it's a lot of data, I think you can really do a pretty good job of interpreting CDFs when they're all piled on top of one another. So the warmer colors here are these older Ordovician samples in Paleozoic, and then moving toward younger and younger and younger. And again, analytical uncertainty is not incorporated here, but you can really easily see that, okay, well, these are dominated by the younger samples are dominated by these young ages, and the older are dominated by this, say, 1,000 million year group of ages. But they're all scaled the same way. And I think that's really one of the powerful things about a CDF. Let's move on to the Gulf of Mexico. This is a data set that Glenn compiled, and he was kind enough to contribute to a paper that Joel took the lead on that came out last year. So Glenn put a bunch of time into putting together this data. And the point of this is to show what happens when you have a lot of data. And so if you say you have over 100, excuse me, samples, so here are 111 samples from this data set. And so that's a probability density plot. That's a kernel density estimate. And so you're not gonna see a whole lot of difference there, right? Between these two. So this is really the major motivation for moving into a more a quantitative evaluation of these data, because clearly you're not going to be able to, unless you take this apart and look at different groups or something, you're not going to be able to interpret this very easily. And that's the same for CDFs. Even with as nice as CDFs are, because they're all scaled the same way, it's going to be pretty hard to interpret or say anything very meaningful geologically about these data. So what to do, right? What should I use? Hopefully I've made it somewhat clear that each of these different types of visualization techniques or methods has its strengths and weaknesses. Probability density plots, kernel density estimates, yeah, it's pick your poison, right? So PDPs tend to oversmooth the older ages, but they have spiky young ones, whereas KDEs are the exact opposite. So they will oversmooth the young and undersmooth the old. And at the end of the day, you're just trying to say something about the rocks, right? So it's really whatever you can, if you're going to interpret your data in a visual fashion like did here, you just want to pick the most representative and whatever will actually show you something. Uncertainties, PDPs, out of everything I showed today, are the only ones that do incorporate analytical uncertainty, and that can be a good or a bad thing. And there's, as you saw with the Cenozoic data in the Andes, the PDPs kind of, they made it a little more difficult to interpret that data. Yeah, so KDEs and CDFs do not incorporate analytical uncertainty. And there's a lot of argument in literature over the past handful of years, so I encourage you to read. I think we put a folder in the short course materials called literature, and there's all kinds of fun papers to read, and you can get a little more out of that. Large data sets. I maintain that I really like CDFs. I think they're an effective way as kind of a first go at a data set. I'll look at CDFs usually first and KDEs and PDPs maybe second, because I can look at a lot of data at once. But is there a better way? Absolutely, right? That's what this course is all about. So we're going to move very quickly into quantitative methods that I think Joel's going to talk about, and perhaps Glenn's going to talk about for detrital pi after me. But yeah, absolutely, there's a better way. So when although I do look at CDFs, usually I'll throw a CDF up if it's a compilation of data I've never seen before, but I very quickly go into a quantitative world where I start making comparison matrices and MDS plots and all this stuff, and it really makes it an objective interpretation at the end of the day. Cool, I think I have 1 minute if anybody has questions. Let's keep them, why not? Okay.
So Kurt, there are a couple of questions that have popped up. Does it affect the peak age when we make adjustments of the bandwidth for KDEs?
Yeah, in a little bit. It depends on what you do to it, right? If you're going to move that, say you have 10 ages very close to one another, if you specify a huge bandwidth, right, and it's going to affect the sum of all of those Gaussians, right? So it might, I suspect it would move it around a little bit, but not a ton. It's very easy to get a different, if say you have just a couple of very young ages and you go PDP versus KDE, you can very easily move the summation, the mode from the summation of those around if you use the analytical uncertainty. So if you look at some of the earlier literature, they would use peak age, and actually a lot of people still use peak age of PDPs. I mean, people do it here at LaserCron all the time. And yeah, I mean, if you have only one analysis down there, that gets kind of scary. So you can start to, that's not going to change really the mean, median, and mode, because you're only dealing with one age. But if you have multiple sitting on top of each other, I think you have to be careful.